Okay, so now we're going to move into Chapter 9D notes. And this is going to be a longer set of notes, so I'll probably break this down into more videos. And we're going to use an exciting example here, the Donner Party. I already talked about this a little bit a few sets of notes ago. And this is an interesting story that features about 90 American pioneers in the mid-1800s. They were trying to get to California, but they got stuck in the Sierra Nevada mountains over the winter. And this wasn't a good place for them to be stuck. Almost half of them starved to death. And just to add a little bit of intrigue to the story, there is evidence that some of them resorted to cannibalism. So this story features cannibals and zombies. Yeah, maybe not really zombies, but but anthropologists have looked at these data and have noticed that females were able to better withstand the conditions than males, and they want to know why, or fewer females died than males. So we're going to expand what we've talked about a little bit with logistic regression, and hopefully there will be enough repeat here as well to help reinforce what we've already talked about in terms of logistic regression. We're not going to go too much further than this. So here is some proc logistic code. The data Donner are on Moodle, if you'd like to try this out for yourself. And if we look at those data, let me just bring those up. So the Donner data are here on Moodle, and you know that we have, you'll notice that we have a name variable, multifamily. This is an indicator variable for whether there are multifamily members with each particular person, the age of the person, their sex, and whether or not they survived. So the survival here is going to be our response of interest. And let's go ahead and model. I'm going to model the event that survived, or that the person survived. We could also model the event that they died, and I think I'll show you below that you get similar models for the two things, just inverse models. You'll get a chance to try that out on the homework as well. And I'm also going to go ahead and output a data set that I'm going to call MyOut. This is a new data set, and you can name it whatever you want. I'm calling it MyOut, and I'm asking for the predicted values, and you can use either P, or you can use pred or predict. SAS will understand any of those. And I'm just naming them P. These are the predicted probabilities that will be output to my data set, MyOut. Okay. So if I run this in SAS, as you saw before, we'll get a lot of extra output. But I want to concentrate on the estimates of the model parameters. And again, I'm going to fit a model. Right now I'm just going to model a simple logistic regression. I'm modeling the probability of surviving as a function of age. And so our model is going to have two parameters, an intercept and a slope for age. Okay. So my equation for on the logit scale, and remember logit just stands for log odds, is simply 1.8183 minus 0.0665 times age. So just looking at this off the top, again, we don't usually interpret the parameters too much on the logit scale, but off the top, this seems to imply that as the folks in the Donner Party got older, the older folks were less likely to survive. That makes sense, right? In general, older folks tend to be less likely to survive. Now I say, what is the equation to compute the predicted odds? So now I want to ask, what's the equation on the odds scale? And odds, we can put a hat on it, since it's using the sample data to predict the odds. And remember, to get from the log odds scale to the odds scale, we just have to exponentiate. We just take e to the 1.8183 minus 0.0665 times age. So then, what are the predicted odds of survival at age 20? Okay, so I'll do that over here. So at age equals 20, we have e to the 1.8183 minus 0.0665 times 20. You can plug that value in. And if you do that calculation, you'll find it's 1.63. What about at age 21? At age 21, we can plug that in. E to the 1.8183 minus 0.0665 times 21. So if you plug that in, you'll get 1.52. So you see the odds of survival decreases as a person, for somebody 21 compared to somebody who was 20. So as the person gets older, as people age, the odds of survival decreases. We're going to define the odds ratio. We've already talked about this, but here's just a refresher for you. To find the odds ratio, we're going to compare the odds of two groups or two values, or at two values, so we can compute the odds ratio. So what is the odds of survival at age 21, which I'm going to put in the numerator, to age 20? I'm going to put that in the denominator. So the odds ratio, and again, if we want, we can put a hat over that, because this is estimated from our model, from our sample data. But this is the odds at 21 relative to the odds at 20. And we just calculated that up above, 1.52, 1.63, and if you calculate that out, it's 0.936. And just to go back to the SAS output, for logistic regression, Proclogistic will generally produce this odds ratio estimates table. And here, for the odds ratio for age, 0.936, that's the same thing that we calculated down here. And note that that's interpreted as for every 1 year increase in age. So for each additional year in age, it multiplies the odds, and this is a multiplication problem, so it multiplies the odds of survival by 0.936. So what does that mean? This means that each additional year reduces the odds of survival by, we can do this calculation, 1 minus 0.936 times 100%, or 6.4, it's about 6.4%. I'll put squiggles there because it's about that, right? So this is a reduction in survival as you get older because the odds ratio is less than 1. So if this is a multiplication problem, if we multiply by something less than 1, we're reducing the odds of survival. If the odds ratio is greater than 1, that would imply an increase in survival. So, and where did this last formula come from? Just to remind you, and I flipped the sign around, but for a relative, we can interpret odds ratios in terms of relative increase or relative decrease. If we take e to b1 minus 1 times 100%, this is the percentage, or the relative percentage, change in the odds. So if I flip this around, I would get a negative 6.4%, which means that the odds are reduced for every additional year of age. So hopefully that makes sense. This is again simple linear regression. So we've talked about this already. Okay, simple linear regression with one x variable. But let's see what happens now. Let's put another x variable in there. And I'm going to make it a categorical x variable. So now let's use a multiple logistic regression. So we have more than 1x, more than 1x, just like for multiple linear regression. Okay. So now let's examine multiple linear regression where we're trying to predict survival based on both age and sex. And so sex is a variable that is actually, if we look in the data set, let me just see my data set here. Sex is already coded as 0 and 1, as is multifam. So I don't have to create a dummy variable here. And I don't have to use a class statement. Logistic does have a class statement, as you saw in the last set of notes, but here I already have a 0, 1 variable. And just a word of caution, so sex is a categorical variable. If we decide to put that in a class statement, if we didn't tell SAS which reference cell to use, SAS would actually use 1 as a reference cell. So it could, in a way, it would code zeros as 1s and 1s as 0s. So it can be a little bit confusing, so be careful about that. Because again, class does everything in alphanumeric order. So sex, again, is already coded as 1 for males and 0 for females. So here's the output that we would get. And again, I'm asking for an output data set that has the predicted probabilities for each age by sex combination in our data set. So here's the output that we would get from this. These are the parameter estimates again. So now we have a beta 0 hat. That's our intercept. We have a beta 1 hat, which is the slope for age. And we have a beta 2 hat, which again we could call a slope, or it's just the effect for sex. So again, you can see if 1 is equal to males, it's not looking good for males in this data set. So now what is the model for predicted log odds of survival? Log odds, remember, is the same as logit, which is what we're directly modeling in logistic regression. So 3.2304 minus 0.0782 is my beta 0 hat, or beta 1 hat, sorry, times age, minus 1.5973 times sex, where remember sex is 1 for males. And again, this is the logit you can think of as, it's also, that's just a shortcut for saying the log odds. So now using this model, predict the log odds of survival for a male that is 23 years old. So we can say logit p hat in this case is going to be 3.2304 minus 0.0782 times 23 years old. Sex is equal to 1 for males, so minus 1.5973 times 1, if you will. And if you multiply that out, I believe you'll get negative 0.1655. So how do we interpret the coefficient of sex? Interpreting it on the log odds scale is pretty difficult. So what I'm going to do is convert it to the odds scale. So e to minus 1.5973. Remember that converting it to the log odds scale, we just have to exponentiate the parameter estimate. And that would give us 0.202. Remember, on the odds scale, so I'm switching here to the odds scale to help with interpretation. This is actually an odds ratio. So we can interpret this as the odds of surviving for males is 0.202 times, so 1/5 about, the odds of surviving for females. Of the same age. Okay, because this is a multiple logistic regression model, so just like for multiple linear regression, we have to assume that the other variables, in this case age, is held constant. It wouldn't make sense to say that a 20-year-old male, the odds for a 20-year-old male is 2.2 times the odds of surviving for a 90-year-old female. That just wouldn't make any sense. But if we compare males and females of the same age, then this makes sense. I just want to say that, so I'm modeling the odds for males relative to females, and note that we could actually flip this all around, and I'm going to give you a chance to try this. So I'm just going to say here, note, actually I'll write this in a different color pen, just to clarify, or try to clarify. If I take 1/202, this is the odds for males relative to females. If I take 1/202, that will give me the odds the other way around for females relative to males, 1.494. So you can also interpret this the other way around, if you're so inclined. You can say, so females have 4.94 times the odds of surviving than males of the same age. I ran out of room, so I'm not going to rate that all out. And notice that what we calculated here is the same thing up here that SAS gives you for the point estimate for the odds ratios for sex. So this is just e to the minus 1.5973 is equal to that. So this is the caution that I mentioned up above. If we add the class statement before the model and I don't specify a reference cell, SAS does everything alphanumerically. So, and it's very similar to ProcGLM. So remember that sex is a categorical variable, but it's already scored 0, 1. But SAS will, again, if we don't specify a reference cell, SAS does everything alphanumerically, so it will model sex equals 0 for females as the reference category, and males will become, males will now be the reference category. Sex equals 1 will be the reference category, and it will give us a dummy variable in a sense for sex equals 0. So it's kind of odd. And notice that it's actually modeling or the estimate for females is just negative estimate for males, which makes sense if you think about it. If you remember what exponentiating a negative value does, it puts it in the denominator or flips it around, the reciprocal. So that's what's happening here. And so if we exponentiate that, we get 4.94, just like we said we would get up here if we take 1 over 0.202. So you have to be careful. You have to understand, make sure that you understand what is the reference cell in the model that you're fitting. So what's the predicted log odds of survival based on this new output? And again, this is an equivalent model. But now the males are the reference in this new model rather than the females. 0.0782 times age, so that hasn't changed at all. The age slope is exactly the same, plus 1.5973. And just for fun, I'm going to rate this as an indicator variable. It's another way, I'm trying to rate sex equals female here. So this is just another way to write dummy variables. It's a shorthand way to write dummy variables. And this means equals 1 if sex equals female, and it equals 0 if sex equals male. So again, the reason I'm showing you this is the exact same model we've had above, or it's an equivalent model. But if I use the class statement, SAS will define the dummy variables for me in the opposite way that I wanted to define them. And so now I use this model, predict the log odds of survival for a male that is 23 years old. So log odds again, logit p hat equals 1.6331 minus 0.0782 times 23. Now, this indicator is now for females, so this is all we have to write for a male that's 23 years old. And if you calculate that out, you get negative 0.1655, which is really the same answer that we got up here above. So I just wanted to show you that it doesn't matter which level you define as your reference category for categorical variables. You'll get the equivalent model, but you as the user have to understand what it is that you're doing. I'm just going to go a little bit further with this example. What is the predicted probability? What is the predicted probability that a 23-year-old male survives? So once we have our log odds, remember that P equals odds over 1 plus odds. And if we have log odds, to get odds, we just have to exponentiate. So the predicted probability now, we're going from the log odds scale to the probability scale. We can take e to minus 0.1655 would be the odds for a male to survive, a 23-year-old male, divided by 1 plus e to the minus 0.1655. And if you calculate that, 0.46. So not great. Less than 50% chance. The predicted probability that a 23-year-old male would survive would be about 46%. So that's 46%. What is the predicted probability that a 23-year-old female survived? So using the same model the way I just wrote it up here, and again, I could have used either of the models, but using this version that I wrote up here, we could take e to the 1.6331 minus 0.0782 times 23. Now we're looking at a 23-year-old female, so we have to include plus 1.5973 because it's a female, divide that by 1 plus that whole mess up top there, 1.6331 minus 0.0782 times 23. That's an 8, if you can believe that. Plus 1.5973. So this would be my predicted probability for a 23-year-old female. And if you carefully run that through your calculator, you'll find that that's about 0.81 or 81%. Goodness. So probably that the model predicted probability that a 23-year-old female would survive would be 81%, whereas for a 23-year-old male would be 46%. So is this conclusive proof that women are more apt to survive than men? Well, no, not necessarily. We have to remember this conclusive proof is something that doesn't really exist in applied statistics. If you get into theoretical statistics, you can talk about conclusive proof of something. But this was an observational study. This was a single sample of pioneers heading to California. Okay, so there may be other factors related to survival than just age and sex. We know there are.